Hi, y'all. I'm going to be going through a couple ideas that will really help with recitation number 3 or number 4, part C, part 3, the third question. Okay, so we're going to cover those ideas. I'll give you a couple hints, and then you will be able to ignore the rest of this video because it will be over. Okay, so here is the idea. Let's say we're going around in a circle. Let's say we're on a nice big merry-go-round. Okay. And I'm going to use the circle tool so that it looks like semi-good. Okay. And we're going to move this so that it is centered. Okay. So we're going around a big circle and we're on a merry-go-round. And you start here and then eventually maybe you end up here, and then maybe eventually you end up here, maybe eventually you end up here. And clearly we're going maybe counterclockwise on this circle. Okay, and so counterclockwise, as you may recall from pre-calculus, tends to be the positive direction, going around the circle. Okay, and clockwise would be the negative direction. Okay, and so as I'm going around the circle, you might have a couple natural questions. One of those questions might be, how far did I go? Well, how far from what? How far from your starting point? How far from the center? How far from the school? You know, whatever questions you have. You have to sort of make a definition. And so in pre-calc, what you'll do is you'll say, okay, well, we'll call this 0. But 0 what? Well, maybe what I want to find out is how fast or how far I'm going around the rim. And so if I were to consider the distance around the rim, well, it's dependent on a couple factors. So maybe we want to consider distance around the rim, around the edge of this merry-go-round. Well, the first thing to note is that we have our very trusty and familiar friend, the radius. Okay, so we have the radius there, and what we have is a counterclockwise rotation, and I want to be able to figure out how far I went around the circle based on the radius of this circle. We'll call it r. And this might remind you of something called arc length. Okay, and so I want to figure out how far along I went, how much distance, perhaps in terms of meters, perhaps in terms of radians. Well, we'll talk about that in a second, but how far in terms of meters did I go? I mean, to some extent, that depends on, let's say I'm at this point. I could just say, well, I went a certain number of meters around, but it feels a little more natural to be able to say I went some angle around. So I went some angle around this circle at any given time. So if I want to talk about, in fact, not just distance, but let's just talk about position. If we consider position around the rim, a very convenient way of talking about that is by angle. Okay, and so I might say that given enough time, I might be a certain angle around the rim. I would call this my angular position. And so my angular position would be some function of theta, or some function of time called theta, right? My angle with respect to time is equal to maybe, let's say, 5. Well, this would mean that And typically this might be a radian measurement, so I might say radians. And that means for all time, I'm at position 5 radians, and 5 radians would be, well, we have 2 pi radians around, so 5 radians would be something around here, maybe. So I'd be stuck here for all time. Oh, or 5t radians. 5t radians means that at time 0, I'd be at 0 radians. And then at time 1, I'd be at 5 radians. And in between, I'd be at various points in a linear way related to the radians. Okay, that's sort of useful if I'm talking about circles, but I still have this radius measurement here. Remember, a radian is the length of one radius as it's wrapped around the arc of the circle, the edge of the circle, or not the edge of the circle itself. Remember, a circle is that ring. It's not the stuff inside. When we talk about the area of a circle, we're saying, oh, the area enclosed by a circle. So that's neither here nor there. So you could imagine I have some angular position. And if I want to convert between like, what's an actual meter number and the angle, well, that will really depend on this radius. And, you know, the first thing to consider might be how many meters in a total circle. Well, the number of meters in a total circle, the circumference, would be 2 pi times the radius, where the radius might be 5 meters. So the radius is in meters. And so this circumference would be in meters because there's no unit on pi or on 2. So this would be something like, okay, well, if my radius were 1, then I'd have 2 pi meters going around. If my radius were 2 meters, I'd have, you know, 4 pi meters around. So that's one way of thinking about their circumference. And then we have to consider, okay, well, what fraction of, you know, the full circle are we going around with? You know, if we are, so this is the total, right? And, you know, I might consider, okay, well, you know, but really I'm at 3/4 of that because I'm at, for example, 3/2 pi. If this is my angle, 3/2 pi, say theta equals 3/2 pi. Let's give that an example. Okay, so if theta is 3/2 pi, then how far have I gone around? Well, I've gone 3/4 of the total radius, right? So I know the fraction of this, or 3/4 of the total circumference. So if the circumference is 2 pi r, I'm going to multiply that by some fraction of it, which is really just, you know, this out of 2 pi. And so I'm at, so what I'd end up getting is that 2 pi r, my total circumference, times 3/4 is equal to my actual position s around, where s is this distance, forgive the line, is that distance in meters. So this is a meters measurement. And so really what I end up finding is that my total distance is equal to theta, right, the angle, effectively. And I can look at this in a slightly different way. If I look at this again, I could say, okay, well, 2 pi r times my angle, which is something times pi, let's call it theta on top, divided by the total circumference, 2 pi. Well, you'll notice I get rid of an awful lot of this, and this ends up being my S value. The top part is my angle, and then the rest cancels out. And so the S value is really just theta r. So this is a conversion. What does this do? It converts between angular location or angular position and linear position. Perhaps not linear, perhaps some sort of metric value, but really arc length, effectively, my arc position. So where on the arc am I in terms of meters? Can I convert that into angle? Sure. In fact, this, using some algebra, so this is a version of it. The other version is that theta equals S over R. So if I know how far along the circumference I am, and I just divide by the radius, I get my angle. So these identities, these ideas are just based on circle math, and they're pretty important. Okay. So this is sort of definitional in terms of position. How do I determine my position around? Well, if I know the angle and the radius, I just multiply them. How do I determine my position in terms of an angle? Well, if I know how far around I am, I divide that by the radius. Okay, so this is my first set. Now, so that's angular position. It's just some function of t, perhaps, and maybe I just have a number for it, a particular location. That particular location can be converted back and forth between radians and meters. This should not be news. This is something you've done in pre-calc. Okay. The next thing that I want to talk about is angular velocity. Okay. So what is it? I mean, we have some sense about angular position, perhaps. Really, how far am I opened up? Let's change this back to red. Okay. And you might have, here's my radius. And what might be the case is I've opened up a certain amount. And I am now at some angle theta. I've opened up by some angle theta. I was here, now I'm here, point A, point B, now I'm at theta. You could say A is represented by theta 1 and B is represented by theta 2. So I could find the difference between them to find out how far I went or how much angle I actually moved by. So I have two thetas. Maybe I could say that my theta, my delta theta, my change in angle, change in angular position, is equal to theta 2 minus theta 1, and that's it. That's my change. In this case, it's B minus A, if B and A are angular positions. Okay, so that should be pretty intuitive. This is, I open up my start minus my end. If I call this, I call this position the position represented by theta 2, and this the position represented by theta 1. This is a new example. Let's in fact look at a new example and get rid of some of this blue. Let's move to a green. Let's say I was opened up this far. Let's call that theta 1. In fact, really, theta 1 isn't that position. Theta 1 is this angle here. And I want to open up again, and I want to open up further, and I want to end up at, say, this pink theta 2 position, where theta 2 is the angle here. In order to find out, let's say if this is where I start, theta 1, and where I end is theta 2, I was over in the upper left, and then I went further down because I'm spinning this way maybe. What I can figure out is that in this case, my delta theta is equal to theta 2 minus theta 1, just the difference between the angles. Just for consistency. So that theta 2 minus theta 1 is really, if I want to make this sort of a different color here, that's really just this angle here. That's my delta theta, the difference between those two. Okay, so that shouldn't be particularly surprising. It should be reasonably intuitive. Okay, now we're going to move on and we're going to talk about angular velocity. So sometimes it's not enough to just worry about angular displacement, and I would call this very much this is my angular displacement. Just like linear displacement is x2 minus x1 or delta x, for example, or delta y, angular displacement is delta theta. How much did my theta change from the start to the end? Angular distance would just be the total journey. You know, if I go back and forth and then around and then back and forth, I'd have to keep track of all of those moves, and that would be my angular distance. But in this case, I have angular displacement. And what if I suddenly worry about how fast that's happening? I want to know what my angular displacement is with respect to time, or with, over time. And so what I'd say is, okay, so I opened up by theta. But how fast did I open up by theta? How much time did it take? And how much theta per unit time did I get? Really what I want to know is how much my theta changed per change in time. Let's say in 1 second, how much did I open up? In 2 seconds, how much did I open up? In 3 seconds, how much did I open up? And this is what I'd call my angular velocity. Okay, so just to define the idea, this is angular velocity. And then we can clearly extrapolate from this. Well, what would I call my angular acceleration? How fast that that angular velocity is changing. So in this case, I'd call it alpha. And I'm putting the bar above because right now we're dealing with average values because these are the non-calculus versions. But if I say angular acceleration, which is alpha, this is omega, and this is theta. So angular displacement, angular velocity, angular acceleration, important ideas. It looks like a little fish. Okay, so we have this alpha, and I'm on this merry-go-round, and I've opened up a certain displacement, a certain angle in a certain amount of time. So I've gone a certain angular speed. And maybe that was varying. Maybe it wasn't, but maybe it was varying. And so therefore, I want to say, well, the delta omega with respect to time is my angular acceleration. And to be clear, this is omega 2 or theta 2 minus theta 1 over t2 minus t1. And we can see this is very familiar stuff. It's really just a slope. And therefore, we can represent it with a derivative if we so wished. And here, omega 2 minus omega 1, how fast was I going at the start, minus how fast was I going at the end. That is my alpha. Okay, so I have angular displacement, I have angular velocity, I have angular acceleration. And just to be clear, I can convert these as well in exactly the same way. We learned from the other page that theta, these are my conversions. And these conversions are angular to linear. Theta is equal to And actually, I'm going to say theta is equal to S over R. Omega is equal to V over R. Huh, that's interesting. And then alpha is equal to A over R, just as conversions. That's how do I move from the linear version to the radian version, the meters version to the radian version. And then when I talk about the linear, I'm going to say that S is equal to omega R just by algebra. And V is equal to, theta R. V is equal to omega R just by algebra. And then A is equal to alpha R by algebra. I just, do my algebra business and then I'm happy. Okay. So I have alpha R equals A, omega R equals V, and theta R equals S, S being the position around the edge. We're talking about position, we're talking about velocity, and we're talking about acceleration. Angular and linear. Okay, and so we have conversions. So this is a nice table to memorize. It's really not hard. You can rederive it anytime you want. But sometimes we'll be substituting these values in to equations that we get from the right side, the definitions of these things. Okay. And so you can probably see where this is going. These are extremely similar to the linear values. And therefore, we could say, okay, well, maybe I have a theta with respect to time, and it's represented, 3t squared minus 2t plus 1. And then I might say, well, what's an expression for omega with respect to time? This is my position, this is my velocity, this is my acceleration, and these are angular. And so my velocity, my angular velocity, I can get simply by differentiating. I use the power rule to get 6t plus, not plus, minus 2. And my alpha with respect to time is equal to 6. So I have a constant acceleration, a linear velocity, and a quadratic position with respect to time for my angular values. And certainly if I want to relate these things together, I can maybe plug in and convert to the linear values, given I know a radius. Okay. So hopefully this sort of makes some sense. So I'm going to give an example problem, and maybe I'll look at 2 other problems. But here's one problem is to say, okay, well, let's say I have a circle of radius 10 meters. Oh man, numbers, it's crazy. Okay, and I know that my angular acceleration is equal to 5t, if I consider this to be with respect to time. It's equal to 5t, and that's a radian value, and this is an angular acceleration. So I want to know what is my, you know what, let's say what's my angular displacement with respect to time in, let's say in the first second. Okay, so what's my angular displacement in my first second? What does that mean? I'm in a circle of radius r, and I'm going around with some acceleration. I know it's positive because this is positive. I'm assuming I start at 0 for this problem. And so I open up and I want to know where I end up after 1 second. Well, I haven't given you angular position value. And so that becomes annoying because how do I figure this out? Well, just the same way I'd figure out another value, the linear values in say, just linear kinematics. I'd integrate. And so in this case, I'd find that my omega of t is equal to the integral of alpha t dt. And here I'm going to consider this to be a definite integral. The definite integral being over time 0 to time 1. I want to know what the value is. Just as a reminder, when I consider an indefinite integral, I get an expression. When I consider a definite integral, I get a number out of the end. And so a number out of the end is what I'm looking for. And so what about this expression? Well, the way or the value. Well, here's the thing. Actually, maybe I don't want to find this quite yet. Maybe I want an expression for my position. So what I'll get from this is that omega of t is equal to the integral of 5t dt, and therefore that's equal to 5 halves t squared plus c, or plus my initial velocity. So maybe, which I'm going to say that omega at 0 is 0, just to remind us. So I'm not moving at the start. And so this c would just be 0. And now I want to consider what my position is, my angular position. And to be clear, theta of 0 is also going to be 0 radians. I'm going to start over here. Okay. And so my displacement is really easy. It's just my position at the end. And so what I'm going to find out here is that, and I could do this in two ways. I'll do it in the indefinite way and I'll do it in the definite way. Okay, so now I want to know my theta of t, but that's just the integral of omega t dt, which is here equal to the integral of 5 t squared over 2 dt, which is just 5/6 t cubed plus theta 0, my starting position. But this is just 0 from above. And so I'll find that my theta of t is just 5/6 t to the third. Okay, so I have 5/6 t to the third, and I want to plug in 1 to this, and I want to plug in 0. In fact, I can say that my difference here is just theta of 1 minus theta of 0. And we can see a connection between the definite integral and this in just a moment, but this is really saying theta 2 minus theta 1, which is just my angular displacement. Well, if I plug in 1 to this expression, I get 5/6, and this is a radian value. And I plug in a 0 and I get 0. So that's equal to 5/6, which is my angular displacement. 5/6 radians. Important to include the radians part. Okay. Now, another way to consider this is to say that that's equal to the integral from 0 to 1 of omega t dt. This is a definite integral. And here I know that that's equal to the integral from 0 to 1 of 5 halves t cubed, or t squared dt. And I'm going to draw up here because I have space. And this is equal to, just to be a little easy, we're going to pull out that front. We're going to say it's the integral of 0 to 1 of t squared dt. And this is equal to 5 halves of t cubed over 3. But evaluated from 0 to 1. And when I evaluate from 0 to 1, what that means is I plug in the 1 and then I subtract the 0. And so what I'll get is 5 halves of 1 cubed over 3 minus, now let me erase this t looking thing. Well, that was super effective. Okay, so this is 1 cubed over 3 minus 0 cubed over 3. Notice what I did was I plugged this in and then I subtracted plugging this in. This is the expression at 1. This is the expression at 0. And that's in fact exactly what we did down here, just without the formal notations. And so I plugged that in. It's just 1/3, 5 halves times 1/3, which is 5/6. Okay. Now, considering this is in radians. What's my actual displacement then? What's my linear displacement? Or my displacement around the edge of the circle? And what I'll find out is that it's, considering what's my S length, what's my arc length here? And the length is just going to be using my conversion factor of theta equals S over R, or theta R equals S, S being that length around. And that means theta is 5/6 times my radius, which is 10. And 5/6 radians times 10 meters is just going to be 56 meters. And so that means if this is a 10-meter merry-go-round, I've gone 56 meters around, which is slightly less than 10 meters. So that's what, 25 thirds. So slightly more than 8. So 8 1/3 meters around. And so my angular displacement is just 5/6 radians. My linear displacement, or my displacement around the arc, around the edge of the circle, is 25 meters. Okay, and so there's a use of the conversion. I could do this with omega, and I could say, well, what's my speed at time 1? Well, at time 1, I was at 0, and now I'm plugging in 1. So if I want to do speed at time 1, I have an expression for the speed, which is just 5 halves t squared plus 0. So if I plug in 1, omega of 1, I'll find that my speed at that time is 5 halves. What's the unit? Radians per second squared, or not per second squared, radians per second. How do I convert this to a velocity? The velocity I'd consider at that point is a tangential velocity. And I'll plug in my value and I'll say, okay, well, I know that V equals omega R. And so therefore V equals 5 halves times 10 meters. This is 5 halves radians per second. So 5 halves radians per second times 10 meters is 50 halves meters per second. And so that's just 25 meters per second. And that's my speed, my finishing speed. My finishing speed tangential to the circle is going to be 25 meters per second. That's a linear value. And what I would consider that to be, that's my VT, my tangential velocity. If I were to suddenly break off my string here, I'd go in a direction tangent to the circle at 25 meters per second. Okay. Third, I had my A of t, remember my A, an alpha of t, and I'll change back to, let's look at, what was the color there? Not that it matters, green, okay. So let's look at that green. Alpha of t is 5t. I know that maybe I want to know alpha of 1. Well, that's just 5, and the unit is radians per second squared. And if I want it, so this is angular. The angular accel at 1 second is 5 radians per second squared. And note, the positive value here indicates I'm moving counterclockwise. And I might ask you to define, are you moving counterclockwise or clockwise? Now, what is my A at 1? What's my acceleration at 1? Well, my acceleration at 1 is just going to be equal to my alpha at 1 times r, where r is in meters. So that's the my A at 1 is going to be alpha 5 rad per second squared times 10 meters. And that's just 50 meters over second squared. That's my alpha at 1. And so, or not my alpha at 1, that's my A at 1. My alpha is saying, hey, I'm opening up 5 radians every second squared, so per second per second. So after a second, 5t radians per second squared. So after a second, I'm opening up at 5 radians per second squared. But 5 radians is a decent distance. That's most of the circle. And our circle has a circumference. Our circle had a radius of 10. Therefore, the circumference is 2 pi times 10, which is 20 pi, which is about 60.2 or 62, 0.8 meters. So circumference is almost is more than 60 meters, and we're going, we're at an acceleration where our velocity is changing by 50 of those meters per second 50 meters per second. It's adding every second. And so therefore, I'm speeding up pretty fast here, is the whole point. I would not be able to hang on to this merry-go-round. Okay. So that's a crash course in angular values. We're going to keep coming back to this, so it's something important to pay attention to. So here's where it comes into my problem. I have one of these spinny things, and I'm moving at some angular speed around, and I have my back to the back, and the floor is falling out. And I must have some force to the center, which is centripetal force. I know that centripetal force can be represented by mv squared over r. Sometimes, however, it might be nice to take that conversion where omega equals v over r, or v equals omega r. They mean the same thing. And say, what if I want this centripetal force in terms of my angular value? Well, the centripetal force is also representable by m omega r squared. I'm just plugging this in for that divided by r. And so the centripetal force is really just m omega squared r squared over r, which is just m omega squared r. That's another expression for centripetal force that's equivalent to this one, just in angular values. So if I know my angular speed, I'd use this one. If I know my linear speed, I'd use this one. Sometimes you'll know one, sometimes you'll know another. And so you choose your values correctly. Another thing to pay attention to is I can always differentiate these things and integrate these things and come up with different values. Different quantities, different represented quantities. I can remove the m and I get a. My AC, if I were to draw a nice circle here and sort of show all these values. So my circle is here. I have some sort of radius r. It's my radius. And I want to know, okay, well, at any given point, let's say I choose a point here and it's blue. So let's say I'm right here. My angular position is theta. How far have I opened up from the 0? Okay. My velocity tangential, my tangential velocity, I'll make this red, is pointing that way if I'm opening up counterclockwise. Okay, this is my VT. My tangential, in fact, I'll label it capital T, my tangential velocity. In fact, sometimes, you might see that as V perpendicular, but tangential velocity is fine. And what that means is that this is, there's actually a 90-degree angle between the radius that extends there and the velocity itself. Additionally, you might notice that the angular acceleration, well, I'm not going to draw that yet, but I certainly know that the angular, the linear acceleration here, I might label this to be AT, or A perpendicular. My A tangential or my A perpendicular are the ones that are perpendicular to the radius. And it's going to line up again in maybe one direction, maybe another, depending. It'll either point this way to the right, maybe instead I have a different situation and it points this way, but either way, it's going to also have a right angle to the radius. Now the final thing in this centripetal value, and I'll do it in orange, my centripetal acceleration lines up this way toward the center. Centripetal acceleration points toward the center always, which means that the force that causes it should point toward the center. That force can be normal force, as it is in this problem. That force can be tension. That force can be gravity. It can be electrostatic force, but typically something that's going to be some sort of pushing or pulling toward the center. Okay. So I have a tangential value, I have a velocity, tangential velocity and acceleration. I have a theta that's opening up. I have an S value. If I really wanted to draw that out, maybe I'll label that in other blue. This is, this is my S. Oh, let's undo that. How far did I open up from there? Up to here. So that's what this arc length represents, how far away I am from that center, or from that 0. Okay. And then finally, I want to consider where are these values? Where's this? I don't see that on here, right? Not A, but alpha. Well, which direction do those point? I mean, velocity points definitely in some direction, right? And acceleration points in some direction. What direction does an angle point? I mean, let's be real. That's kind of weird, right? What about theta? What direction do they point in? Where are those arrows going? Well, it turns out that I'm going to consider either clockwise or counterclockwise to be the direction. So this is going to be a negative value. It's going to be positive. And so if my angle is positive, I have a positive value. And if my angle is negative, I have a negative value, or clockwise, I have a negative value. And these ones, well, if they're positive, maybe they're coming out at me from this circle. And maybe if they're negative, they're going into the circle, because I can't represent them on the plane, because then I'd be pointing in a direction, not clockwise or counterclockwise. An arrow this way means clockwise on this side of the circle, but an arrow this way on this side of the circle pointing the same direction, that would represent counterclockwise, whereas over here it would represent clockwise. Think about that for a second. So I can't just have an arrow on the page. This is wrong. That can't be a representation of these angular values. So either we are going out of the page, showing an arrow head, or into the page, showing an arrow tail. And that's something you might see at the center of a circle, and that might be, my omega might be coming out at my face, my acceleration might be going in to the circle, but those are values that we'll come back to in the future. What you need here, though, is just a sense of centripetal force and how it works, and maybe some values, angular acceleration, angular position, angular velocity. Okay. Hopefully that helps. Goodbye.